Hello again, everybody, and welcome to the Chapter 7 video for Introduction to Logic. So in this chapter, we'll be learning a new concept. The concept is interchange, and pretty much all that we will care about with respect to interchange is interchange of equivalence. It'll make sense when I get there. And so we're going to learn how to replace schemata or parts of schemata with other schemata that are equivalent to the original schemata or parts of schemata. That sounds confusing when I say it. It won't be as confusing when you're doing it, right? So the first section is just some conceptual stuff. And then the rest of what I'm going to be doing is I'm going over some equivalency laws or rules, I guess, that you will use to transform schemata into a different form so that we can perform operations on the new schemata in an easier way than we could on our original schemata. The real reason why you're learning this is because you need to learn how to transform schemata into something called conjunctive normal form, which you'll learn about next week in the next chapter. So right now it might seem like, why are we doing this? It's not important, but it's absolutely essential that you learn how to apply these rules. It's absolutely essential that you get comfortable knowing where you can apply them and where you can't apply them. So I'll give you examples for almost everything. I'll explain them. Yeah. So again, don't panic because we're getting a new set of rules. They're not all that bad. And yeah. So moving on, interchange and interchange of equivalence. Okay, interchange. So interchange is what we call the process that consists in replacing some schema, with another schema when the conditions for substitution are not met. So remember that when we substitute a schema, or we substitute part of a schema for something else, right? We have to replace every occurrence of a letter. If we're substituting something in for P, we have to replace every instance of P, and we have to replace it with the same thing, right? So substitution, if we have the schema P or Q, and we wanted to substitute in for P, I don't know, the conjunction AB, right? To substitute that in for P, we would get AB or Q. So those are the conditions for substitution. Interchange, we can replace anything with anything, right? So let's say we have the schema P or Q, right? For interchange, we could or using interchange, we could turn this into if X, then Y, if and only if Z, right? And so substitution preserves validity and inconsistency. Validity and inconsistency. Right. Interchange ordinarily preserves nothing. Sorry for the awful handwriting. And what that means is that if we start with a schema that's valid and we follow the rules for substitution, so we replace every letter and we replace each letter with the same thing, then if our original schema is valid, the schema that we get through substitution will also be valid. And if it's inconsistent, the schema that we get through substitution will also be inconsistent. With interchange, obviously, since we can replace whatever with whatever, it doesn't preserve anything. The schema that we start with could be consistent. We use interchange and replace it or part of it with something else. We might get something that's valid. We might get something that's inconsistent. We might get another consistent schema, right? So it's impossible to say using interchange it doesn't preserve anything. So if our starting schema is valid or inconsistent, we don't know what we're going to get if we use interchange to replace parts of it, right? So interchange is basically useless in general. So you should never do interchange except for the one special case I'm going to get to in a minute that's very important and very useful. I'm just explaining the definition so you know what it is, right? But there's a special case of interchange known as interchange of equivalence. And so interchange of equivalence is when we replace a schema or part of a schema with another schema that it is logically equivalent to. And the reason why we have this special case, interchange of equivalence, is because interchange of equivalence preserves everything. Oh, that's an awful color. Okay. And so hopefully, if you've been paying attention to the chapter on implication and equivalence, we have a way of testing whether or not a schema or part of a schema is equivalent to some other schema, right? If we wanted to see whether or not, let's say, if P then Q was equivalent to the schema not P or Q, right, we connect them with a biconditional, and if it always comes out true, then they're equivalent. So just in case you don't believe me on that, they are equivalent, by the way. I'm going to do a truth value analysis real quick just to prove it to you. Right, so we drop, I'm doing two steps at once. So we drop true as the antecedent of a conditional, and we drop false as a component of alternation. So we get Q if only if Q, which is true. Then here it's false, therefore Q if only if true or Q. And so we reduce a conditional with a false antecedent to true, and we reduce an alternation with a true component to true. So true, if and only if true, which is true, right? So these two things are equivalent. And that means that anytime we see one of these in a schema, either if P then Q or not P or Q, we can replace it with the other one. And that's what we're going to be learning here. Is I'm just going to be giving you a bunch of really useful equivalencies that you can use interchange on to replace schemata or parts of schemata with other schemata that they are equivalent to. And again, the reason why we have to do this is because it allows us to transform our schemata into forms that make doing tests on them very easy. There's also a tertiary benefit, I suppose, in that if you recognize these equivalencies, you can greatly simplify truth value analysis. So, and again, I'm just going to use the examples from the book here, and that's because I put a lot of thought into designing examples in the book that illustrate kind of a wide range of different applications of this. So if we consider, and again, this is on page, what page? I don't have page numbers. I don't know what page it's on. 49. So as an example of how this can shorten truth value analysis, consider the schema. If P, then Q. Therefore, not P or Q. And not if R then S. Therefore, R and not S. Right? So I'm just going to, you'll get the rule in a minute, but not if P then Q is actually equivalent to, P and not Q, right? So if we know that, right, this would take a while to do if we were to do a full truth value analysis on this whole thing, right? But we saw above that this and this are equivalent, and I just told you, I'll prove it, that this and this are equivalent. So we can make this a really easy truth value analysis if we replace, say, this with this, and if we replace, say, this with this. So using interchange of equivalence, we can transform this into the schemata that I'm going to write. So, or into the schema that I'm going to write. And so we just used interchange of equivalence to do this. We used the two equivalencies that I just showed you, and you'll get a bunch more of them shortly, and we have this schema. And so we still have to take a little shortcut here, but if you remember from our laws concerning implication, right, you'll know that every schema implies itself. And what that means is that if you have a conditional where each side of the conditional in here, these are the conditionals I'm referring to, these ones, right? If you have a conditional where each side of the conditional is the same thing, you know that it's going to reduce to true. That's a shortcut that you'll always be allowed to take. So this reduces to true and true, right? Because this left side of the conjunction, all that is it's the whole left side's one big conditional. It has the same thing in the antecedent and consequent place, so we know it'll reduce to true. The right side, same thing. It's a conditional where the antecedent and the consequent are the same thing, so we know it'll reduce to true. So we can reduce the whole thing to true. That's a lot shorter than the truth value analysis that you would have to have done on the original one. In order to save time, I'm not going to do the truth value analysis to justify every one of the equivalencies that I'm going to tell you. I believe I do for most of them in the book. So if you don't trust me, you can check, or you can do it yourself with the truth value analysis. It just takes forever to go through all the rules and justify them. So what we're going to be doing in the rest of this video, and what you'll have to do in this chapter, is we're going to learn a bunch of these equivalency laws, and we're going to learn how to apply them, right? And again, it's not very difficult. The hardest thing is probably recognizing the grouping with the dot notation to see where they apply. So the first and probably the most important, well-known logical equivalency that I'm going to show you is De Morgan's laws. There are two of them. So I'm moving on to that in a moment. Okay, the first equivalency that we're going to look at is known as De Morgan's first law. It's called this after Augustus de Morgan, who was a famous logician in the 18th century. So the first law states that, I guess in English you would say, the negation of a whole group of alternations, so not P or Q or ... or S, right, is equivalent to if you take all the same letters in the alternation, replace the alternations with a conjunction, negate them, it makes more sense if you see it than if you say it. So this is equivalent to this, ... not S, right? So the simplest example of this, and again, there's a truth value analysis that justifies this case in the book. I promise it actually is valid. So the simplest example is if we take the negation, it's not negation sign. If we take the negation of the alternation P or Q, right, that is, what I'm writing is the assertion of a truth, P and not Q, right? So again, if you have the negation of a group of, the negation of an alternation, right, that's logically equivalent to, means the same thing as if you drop the alternation symbol, replace it with a conjunction, and negate all the original letters, right? So this doesn't just apply to an alternation of two letters. So if we have not P or Q or R, right, that is equivalent to not P and not Q and not R, right? And this is why actually one of the reasons I said in a previous video that we want to translate this as neither nor, right? This is, if we say the words in English, neither nor, so if we P for, like, I don't know, Quine ate a cookie, and Q for Quine ate a pie, right? The negation, if we want to say it's not the case that Quine either ate a cookie or ate a pie, right, we could translate that into our logical language in either of these two ways. So the technical explanation of everything this applies to is it applies to anything that we can get from this simple case right here through substitution. I'm going to work through a sort of small example of this, I guess. So we can actually get the thing I just erased from this through substitution. So remember, in substitution, we replace every occurrence of a letter, and we replace it with the same thing. So let's, again, this might be a little too technical, and maybe we'll just confuse you. I'm only going to do it for this one, just so you can have a full, complete explanation of how this works. So let's replace P here with, through substitution, with P or Q, and let's replace Q here through substitution with R. Oops, spelled that wrong. Right, so if we do that, if we do this substitution, we get not P or Q or R on one side, and on the right side we get not P or Q or R. Did I do that right? Oh, wait, actually, this needs to be a not R because the Q is negated here. Okay. So, again, I promise you, you can check if you want to look at my truth value analysis in the book, that this is valid, and substitution preserves validity, right? So this schema that we get is also valid, and because we know that this up here is valid, we can actually replace this with just not P and not Q, or actually, wait, I screwed up. Sorry, that's probably confusing. That should be a conjunction. Fuck. I don't want to redo this because I've been recording for a few minutes, though. Let me rewrite that. Sorry. I really apologize for that. Right? So we get that on the right side by applying this law to it, right? So P or Q, and we don't need this dot here because we don't need dots inside of, if the only thing going on in a group is alternation, we don't need the dots to mark the different components. Right, so that's kind of how so technically the law applies to everything that we can get from this base case with substitution. Another way of thinking about it would just be to think that it applies to, if you have a conjunction of things that are negated, you can apply it, or if you have the negation of a whole alternation, you can apply it. So I'm going to run through some of the examples in the book just to show you. So if you have, just so you keep track of negation signs, right? Not P or Q, right? So that's equivalent to not P and not Q, right? Because we have this negation sign over the P here. And if you look, we have to negate it. See, like right here, right? So when we apply De Morgan's law to this, we have to keep track of the negation sign and make sure that we double negate P. But if you've been paying attention, a few times I've said that double negations just cancel out. So it's just the negation, it's not the case that not P or Q, right, is equivalent to the conjunction P and not Q, right? So just another example. Again, these are from the book, and I'm not just being lazy here. I actually tried to come up with a bunch of different cases that confuse people. So if we have the negation of P and R or Q and R, right, that is equivalent to, and we can replace it with whenever we want, the conjunction not P and R and not Q and R. And of course, we could apply, oh wait, no, we can't do that. Never mind. It's the second law. Okay. Just as another example, I'm going to go through all of these because it's important that you get this down, is if you have not P and R or the negation of the conjunction Q and R. Oh, we actually have to use brackets here. Right, so that's equivalent to, and you can replace it with, at your leisure, not P and R, and not the conjunction of not P and R and not Q and R. But again, double negations cancel out, so you can just skip right to this if you so desire. Okay. Right, so another maybe more elaborate example is if we have this schema, not P for Q. That's equivalent to not if P then Q conjoined with not if Q then R, right? And all I'm doing is applying this law to different sorts of schemata to show you the various things that you can apply it to, right? So one thing to note about this law is because it's an equivalency, it works in both directions. So far I've been starting with examples like this and going to examples like this. But if you have something that looks like this and you're trying to, for some reason, make it into a negated alternation, it goes both ways. So let's suppose that you have something like not P and not U. The conjunction of it's not the case that P and not U, and it's not the case that R and S, right? So this is equivalent to, and this is an application of the law, it works in both directions. All of these equivalency rules work in both directions. Not P and not U, or R and S. Right. So again, we have a conjunction of two negated things, and that lets us move to something like this. Okay. What's the next one? Okay. It even applies to things that might look like it doesn't apply. You got to remember that we have two different ways of representing negation here. So if we have the schema, it's not the case that if P then Q and not R, right? That is equivalent to, and we can replace it with the schema. I'm not even going to try to say this out loud. It doesn't make any sense when you say this crap in English. Right, because this left-hand side is the conjunction of two negated things. So on the right side, we replace the conjunction with an alternation, and we move the negation signs out into the front of the whole group, right? So if we have something like this, double negated P and Q, we can even apply this to double negation, so to things that are equivalent to non-negated letters, right? This is equivalent to not the case that not P or not Q, right? And so this also, because we know that double negations cancel themselves out, right? The conjunction P and Q is equivalent to the negation of the alternation. I'm not even going to try. It's equivalent to that. Again, when you have like a bunch of negation signs nested, there's just no way to say this stuff. So again, this works in both directions. Study those examples. You probably want to look at the examples in the book for this one. As confusing as it may be, I promise it's not that bad once you get the hang of it. Okay, moving on in a second to De Morgan's second law. Okay, De Morgan's second law. And so 90% of the time, we'll be using these in one direction. And so what this means is if we have the negation of a conjunction, negation of a conjunction inside parentheses, it's equivalent to an alternation of all the same things that are inside the conjunction, but they're negated. So again, I don't know how useful it is for me to try to say this stuff in English, but that's De Morgan's second law, right? So again, the simplest case of this is something like if you just have the negation of P and Q, right? That's equivalent to this, not P or not Q. Right? And I'm not going to go through the whole substitution thing again because I think it just confuses people. If anybody really, really wants me to, I can post a video where I explain in a little bit more detail how that works. But so some other examples of how this works is, remember, we got to keep track of negation signs. That's probably the hardest thing about using these is we have the conjunction, the negation of the conjunction P and not Q. I don't even know why I'm trying. That's equivalent to this, not P or not Q, or because again, double negations cancel out, not P or Q, right? So as another example, and again, just giving you a bunch of these so you can recognize where it applies. It might not be immediately, it's too big, obvious. So if we have the negation of P and not Q and R, so that's equivalent to, and we can replace it with not P or not Q and R. Again, double negations cancel out. You can always just, like, once you get good at this, there's no reason to not just go straight to not P or QR for one like this, right? So again, doesn't just apply to conjunctions with two components. So if we have the conjunction not P, Q, R, S, right? That's equivalent to not P or not Q or not R or not S, right? Similarly, again, these are sort of the same kind of flavor as the examples for De Morgan's first law. If we have this schema, right, that's equivalent to, and we can replace it with, we can replace it, by the way, if it's a component of some larger schema as well. You'll see what I mean. So this is equivalent to not if P then R or not, or sorry, that's a Q. Not. Whoa, sorry. Right. Again, because this inside this negation side, it's a conjunction. It's a conjunction of two conditionals, but it's a conjunction, right? So because it's a conjunction, you could say it shares the same form as the simplest example. More technically, we could get it through substitution from the original example. But anyway, so that is another way of applying De Morgan's second law. Right, so another example that you could run into is, remember this works in both directions. Most of the time we're going to be using it to remove the negation sign from in front of parentheses, but sometimes it might be useful to go in the other direction in like a truth value analysis. So P or Q and... Oh wait, this one actually doesn't go in the opposite direction. I think the next one will. RS, therefore G. I don't know why that has brackets. Anyway, that's equivalent to not P or Q or not R. If R and S, then T. Right, so just another example of how you can apply this. Here's one that actually does work in reverse, I guess, is if we have not Q and R, or not P, right? So this on the left side here looks like it has the same sort of form as the right side of ones like this, or this, or... oh wait, did I scroll down too much? Yeah, this. So, right, this is an alternation where every component of the alternation is negated. And so this would turn into a negated conjunction. It's equivalent to a negated conjunction, and the negated conjunction that it is equivalent to is the negation of Q and R and P, and I'm just leaving the dot in there to make it clear what's going on. Right? It's not the scariest stuff in the world. just one more. The last one's just a lot of writing. I don't know how helpful it is, so I'm just going to do one more. Is if we have this. This is another in reverse one. You got to get used to the fact that these laws work in both directions. Right, so if we have this schema if we have this schema and we want to replace it with an equivalent schema for some reason, what we could do is this turns into this. Again, strictly speaking, this dot isn't necessary. I'm just leaving it to make it clear that conjunction replaces alternation when you apply this rule. Okay. And so, again, most of the time what we're going to be using this for is we're going to be using it, both of our De Morgan's laws, for eliminating things like negated alternations or negated conjunctions, right? So most of the time we're going to be using it to get rid of this this negation sign in front of the parentheses. By the time that we actually need to use it, you'll understand why that's an important thing to be able to do. But that's De Morgan's second law. And so the other laws that I'm going to go through involve conditionals, biconditionals, and the distributivity laws. So moving on, I'm going to give you the law for eliminating negated conditionals. Okay, so the next equivalency we're going to look at is our equivalency rule for eliminating negating conditionals. By the way, the aim of learning all of these is what we're going to do with these equivalencies is we're going to end up removing all of the conditionals, negated conditionals, biconditionals, negated biconditionals. We're going to get everything into just conjunctions and alternations, and that's sort of the game plan for this. Although we won't get to that for, I think, another 3 chapters. Don't worry too much about it. Or we won't get to the application of that for another 3 chapters. So this is our next equivalency law. I don't know why this is 5. I think I just copied Quine's numbering. Anyway, so we have, if we have a negated conditional, such as it's not the case that if P then Q, that's equivalent to this, the conjunction, or wait, no, wrong, bad, P and not Q, right? So if we have a negated conditional, it's equivalent to the conjunction of the antecedent and the consequent negated, right? So again, just to go through some more examples of this, if we have something like, again, these are from the book, but I tried to come up with examples in the book that capture almost every sort of circumstance in which you might run into these, or at least to prepare you pretty well for doing these to a bunch of different schemata. So if we have this conditional, right, that goes to, or actually I'll keep, it's equivalent to this schema. Right, because the conjunction P and R is the antecedent, right? The consequent Q and R is the consequent. And remember, we replace a negated conditional with a conjunction of the antecedent and the negation of the consequent, like so, right? Okay. So again, another example. I guess I can just, I don't know why I'm scrolling down, actually. If we have not P or Q, therefore R. So this is going to be equivalent to this. We don't have to write the negation like that. I mean, we can write it like this, same thing, really. Okay. Another example, I'm just giving you more complex examples so that you don't get scared when you have to apply something that's more complicated than, you know, the base case. So another obnoxious example is if we have this. Wait, why did this is... Okay, never mind. This is obnoxious. I'm not doing this one. Sorry. I think I screwed... There's a dot where there shouldn't be one in the textbook. I need to fix that. My bad. I'm going to do this one instead. Oh, wait, that's negation. So this one is equivalent to this. Right, because the consequent here is already negated, we double negate it here, so not rs. Oh, wait, that should have parentheses. But again, double negations cancel out, so if you wanted to write this PQR and rs, that'd be fine. Also, you know, you could get rid of the dot if you really wanted to. Oops, rs. Right, but anyway, I'll leave the dot. One more that just shows you how it works if you have a negated antecedent is not R. So this is equivalent to not Q and R, right? Because it doesn't change, so it's negated here, and we don't double negate the antecedent. We're applying this equivalency rule, right? So it's not Q and R, but we do negate the consequent, so not R. Okay, and that's how we get rid of negated conditionals. They're not that scary. Next, I'm going to give you the rules. One rule for eliminating biconditionals. Okay, eliminating biconditionals. So if we have a biconditional P if and only if Q, it's equivalent to the conjunction of if P then Q and if Q then P. That is why it is called a biconditional. Fun logic fact is because it's equivalent to the conjunction of two conditionals, right? And I guess one way to think about these is just rules for rewriting schemata. So anywhere you run into this, you can rewrite it as this, right? No problem. Yeah, if the interchange stuff just went over your head and the like substitution explanation like makes you want to smash your face into a wall, these are just rules for rewriting. So anytime we run into a biconditional, we can rewrite it like this if we really want to. Okay? So this does work in both directions. I think I don't have an example that illustrates that, but it does. So you know, just to make up a simpler case of it going in the other direction, right? So if we have this, right, this holds this biconditional, right? Also, the order doesn't matter in a biconditional, so you could also write, right, same thing. Okay. Another example, just, again, showing you simple examples of negation signs because you have to keep track of them. But if you have not P, if and only if Q, right, that's equivalent to... And here I'm reading the biconditional as is logically equivalent to... That's not a good translation in English to English because most people don't understand the concept of logical equivalence. But here I'm explicitly using it to assert that these things are logically equivalent. So that's why I'm reading it that way. So this is equivalent to if not P then Q, and if Q then not P, right? And again, only tricky thing about this is that we have negation signs we got to keep track of. You will screw yourself up horrendously if you drop a negation sign. However, I'm going to instruct the TAs when they're grading your work not to punish you too much for that. I do that. You've probably seen me do that. Everybody makes mistakes, right? So a little bit more complicated example. If we have this, right? So this is equivalent to, and here I'm just using lots of dots to show you that this is the main operator, this biconditional right here. So this is equivalent to P or R, therefore Q, and Q, therefore P or R, right? Again, not super painful. One more, just the hard part about this isn't like recognizing the rule, it's just keeping track of where the dots are and everything. So one more example, if we have P, Q, oh wait, I screwed that up, sorry. So if we have, whoa, that's, I can't write today, I deeply apologize. Q, therefore R, right? So this whole thing is going to be equivalent to, and again, we need more dots here. So this is equivalent to P, therefore Q, therefore R, and Q, therefore R, therefore P. Again, you probably won't run into any that are as tricky as this. I'm just showing them to you so you can see all the sorts of things that this applies to. Right. There's another rule that we use to get rid of biconditionals. You only really need to know one if you know all the other rules, because you can, if you use one, you can get the other form through some more applications of equivalency laws. So the second equivalency, we'll probably use this far less frequently than the other one, asserts that P therefore Q is equivalent to not P and not Q, and not Q and not P. I used this as an example. I did a truth value analysis on this as an example in the like additional implication and equivalence problems. If you want to see the truth value analysis for this, I'm just, so this is obnoxious, and if at all possible, you should use the rule 6 and not rule 7, because if I try to do these, I will lose track of the negation signs and where they're supposed to be. But just one simple example of how this works is if we have this schema, it's equivalent to not, I'm not even going to try to say it. There's no point. Oh, that doesn't need a dot. Oh, and that should have brackets. Yeah. Again, the negation signs are just really tedious. You won't use this one quite as much. Okay. And so next, I'm going to give you the laws for eliminating negated biconditionals. And I just realized that there's an error in the textbook. I accidentally dropped a section when I was compiling this. I now understand why I skipped right from 2 to 5 when I was numbering these. So we also have rules for eliminating conditionals, and I think I forgot to notice this because they're probably the ones that I use the most. So we have 2 laws for eliminating conditionals. The first says that if P then Q is equivalent to this. The second says that if P then Q is equivalent to not P or Q. Again, for what we're going to be doing in this class, 99% of the time you're going to use this one. And it's easy to remember, I think. Right? So just to give you an illustration, if we have, P, Q, P and Q, therefore R, right, that's equivalent to this. Right. It also works in both directions. So if we have, what's a good example? I don't know. Let's do a single letter. Not A or lowercase b, c, d. Right. That's going to be equivalent to, and we can rewrite it whenever we run into it as if A, then B, C, B and C and D, right? This one will actually is different in that we'll actually use this one in both directions. It won't be very complicated, and I'll explain how we go in the opposite direction that we normally would when we get there. Don't worry about it too much. Right, so, both of these are examples of Rule 4. For Rule 3, I mean, you should know that it applies, but I don't think it would ever be really useful to apply it, at least in this direction. Yeah, note that it exists. I'll put it on the rule sheet just in case. And obviously, if we have for the 4th rule for eliminating conditionals, if we have something more complicated like, right, this would be equivalent to, so here the whole thing's a conditional, and this is the antecedent and this is the consequent. So if we're turning it into an alternation, we would negate the whole first part, right, or R. And since we know some other rules at this point, if we wanted to reduce this or to transform it again, this is going to be equivalent to P and not Q or R, right? Yeah, in accordance with our rule for eliminating negated conditionals, which is up here, right? So 4 is an important one. Fortunately, I think it's pretty easy to use. So no 4, 3, maybe not the most important rule. Again, it's good to know it exists and how to apply it. But the fact that I forgot to put it on there shows that it's not that important. But again, 4 is super important. You should learn how to eliminate conditionals because we'll need to do that. Okay, moving on to eliminating negated biconditionals. Okay, getting rid of negated biconditionals. So we have 2 laws here. Pretty straightforward. So if we have not P if and only if Q, that's equivalent to, if I can spell, not P if and only if Q. The other way that we can negate this, don't panic that there are 2 of them. You'll see why in a second. Right. So those are our two rules for negated biconditionals. I'll just give you one simple example of how we could apply both of these. So again, if we have the PQ RS, right? So say we have this negated biconditional. So we could go from that to not P and Q only if R and S, or we could also, it's also equivalent to right. You'll have to use this sometimes, but I think it's pretty straightforward because like the operator doesn't really change or anything. If you have a negated biconditional, you just drop the negation sign and negate one side of your choice. I think it's the only rule I've explained thus far that I can explain it in English and it makes sense. Okay, so I don't think you need a lot of examples for that one. So I'm going to move on to the distributivity laws. I hate these. They give me a headache. You'll need to learn how to do basic cases of them, but because they give me a headache, I don't want to sit there and make up really complicated ones and check them. So anyway, moving on to distributivity. Okay, distributivity. We have two laws of distributivity. I'm going to go through the law of distributivity of conjunction through alternation first. And how this works is if you have a conjunction and one side of the conjunction is, well, anything, and the other side's an alternation, right, that's equivalent to, again, I have no idea how to say this in English, but that. It's pretty similar to, what's a good math? I can't think of a good math example off the top of my head, but I know that you do stuff like this in algebra, right? So if we have, I guess, a simple example of this would be if we have the conjunction of P and Q and the alternation R or S, right? That's equivalent to PQR or PQS. Right, study that. Again, this gives me a headache if I have to do anything that's too much more complicated than that. Yeah, so that's how that works. For another more complicated example, and again, these trip me up sometimes, is if we have. So it might not look like this applies, but technically we could in this substitute P for if P then Q, so it has to apply because this is valid and we could get this from that through substitution, or what I'm going to write here we could get from that through substitution. So this is equivalent to, right? So we do the same thing for this one that we did for this one, except instead of conjoining P and Q with, instead of doing it like that, here, I'll just show you. Again, there's no good way to say this in English. Right, so we get P, oh wait, this needs more dots. Didn't give myself enough space. So we get P or Q and R or and S. Right. Yeah. Just look at that and try to see how it's an application of this rule. It gets a little confusing with the dots. It's not a hard rule to apply. It's just the hard thing is keeping track of how the dots might change the grouping of the formula. So one neat little thing that we can do is if we have something, as Quine points out, if we have a conjunction of two alternations, so if we have P or Q and R or S, right? That's going to be equivalent to, we can do what you're probably familiar with from mathematics as cross multiplying, right? So this is equivalent to PR or PS or QR or QS, right? And so that's how the law of distributivity of conjunction through alternation works. I would show you more work if there were any more work. I would show you intermediary steps if there were any intermediary steps. But you have to kind of study the examples, give it a try. I can post more examples of this if anyone wants it. So that's our first law of distributivity. In a second, I will move on to the second law. Okay, this is our second distributivity law and the last equivalency rule that we need to know. Okay, so this law allows us to, if we have an alternation where one side is anything and the other side's a conjunction, we can distribute the alternation over the conjunction. And so, again, just like a really simple case. So we have P or QR. And you don't need a dot where I just put one, but when you're doing these, it might be useful to be a little more explicit than you need to be with the grouping. So this is equivalent to P or Q and P or R. Right, so the simple cases for these are really easy. It's just the complicated ones can kind of give you a headache. Right, so here's another more complicated example. So if we have the alternation PR or right, so again, we just pretend that this is like the P here, right? You can actually just rewrite, if you wanted to do this in a more easy manner, you could replace this with some like symbol or like, I don't know, like a smiley face, right? And so then you would get, what is it? It's smiley face or Q and smiley face or S and smiley face or T, and then we just, since this was a PR, the conjunction P and R, we just erase our smiley faces and put in the conjunction P and R. I don't know if that's good advice for how to do these, but that's how I actually do really complicated distribution ones, is if I know that one side isn't going to change, if it's like the P here, right, but it's some long complex schema, I'll just put in like a symbol or a picture, a doodle or something to keep track of it. It's easier for me to work with these when you have some visual representation that like one thing's in its own group, right? So another example, again, just to go through these. Oops. If we have P or K, L, conjunction of K and L and R, that's equivalent to P or K and P or L and P or R. Right. So again, we can have some of these that are obnoxious. So I think the last example I had in the book was, let me check. Yeah, this is it. P or, and you're going to be like, why my life? Z then Q and R, right? So what we're doing, so this whole thing is a conjunction, and so I'm going to do my incredibly sophisticated smiley face technique again, and right, so how this works is we get, so P or smiley face, and actually we're going to need a dot there. We don't know that until we plug it back in, but we will. And P or R, right? And so then we replace our smiley face with, what was it? If Z, then Q. Right, and that's how that one turns out. I don't know if the way that I do that is helpful to anybody. It's a lot simpler for me to mentally keep track of, oh, the smiley face goes here. You don't have to use a smiley face. You can just use some like letter from another alphabet, or like some letter that we're not using from our alphabet or whatever. But I think that makes it a little bit more manageable to see it. Again, I'm not super great at doing really complex ones of these. So those are all of our equivalency laws. And what I'm going to do just real quick before finishing the video is I'm going to come up with some really long complex schema that I can apply a bunch of these equivalency transformations to. And hopefully then you'll get a sense of like how they work when applied to parts of schemata, right? So let me think one of those up real quick, and I will finish the video with one of those. Okay, here's my sadistic example, I guess, of a schema that we can apply a lot of our transformation rules to. So what I'm going to try to do is, and hopefully I'll be able to do this without distributing a ton, is I'm going to try to eliminate every conditional, every negated conditional, every negated biconditional, every biconditional, and I'm going to apply De Morgan's laws as much as I can. So I'm going to think through this. So first, right, the whole schema is one big conditional, right? If we're paying attention to our dots, right, this whole thing is the antecedent and this whole thing is the consequent. So I'm going to apply our one of our rules for eliminating conditionals. Where to put it? Yeah, eliminating conditionals. So I'm going to apply this one, rule 4, to the whole thing. So it might help for you to like reference the rule sheet, which I will hopefully remember to post while I'm doing this. So how I would do that is I'm going to negate the whole antecedent, so this whole thing, and that means I'm going to have to put it in brackets like this. Right, and then that we replace the conditional, we're applying this rule with an alternation. That's how we eliminate, one way in which we eliminate conditionals, and the consequence stays the same. So okay. So what can we do now? Well, let's take a look at the left side. I'm just going to do this side by side now because in theory, I should be able to get this to be just alternations if I'm smart. So this left side, right? Well, it's a conjunction, right? We don't have the dot, but because we don't have any, we could put a dot there. It's the conjunction of this and this. So we can apply De Morgan's law, the one that applies to negated conjunctions. So we do that and we get not, if P then Q, and not, Q if and only if R, right? But because we know that double negations cancel out, we can just go right from that to this. So now we have, this is another conjunction, right? Oh, wait, no, it's not. Sorry, I screwed up. That should be an or. Right, so we have an alternation of a conditional and a biconditional. So first, I'm going to do the same thing I did to the whole schema of this conditional. So this isn't a truth value analysis, by the way, so I'm not drawing the lines, but I guess I can just to show you what goes to where. So that gives us not P or Q. Those need dots. Or Q if and only if R. Right? So, okay, so this is as good as it can get if I'm trying to get rid of all the stuff I said I was trying to get rid of. So this biconditional, right, we can get rid of in a few different ways, but I'm going to do R then Q. That's an application of one of our rules for eliminating a biconditional. So we're going to need more dots than we had in the previous line because we want to make sure that we keep track of the fact that this whole side is one big group, right? So then we just put in the left side that we already had. Right. So now I have these two conditionals, and I'm going to apply the same. Oh, wait, that's not negated. Sorry. See, it's really easy to screw up with negation signs, and that's why you won't lose a lot of points for doing that, because I do it all the time. Right. So we can get rid of these two conditionals that we made. And we do that like so. So we get not Q or R, right? Remember, that's our rule 4, I think. And, oops, not R or Q. And so put in our left side. Right? So that is pretty much everything we can do with our left side. We could do some really obnoxious distributing. Not going to do that right now, because to just fully distribute this whole thing would be ridiculously complicated. Okay, so let's look at our right side. Right side. So this is a negated alternation, right? So we can apply one of De Morgan's laws to it. And if we do that, we get not Q and R, and not, because remember, there's already a negation sign here, so we got to double it. Here there's not one, so we need to put one in. P then Q. Right? And once again, it's expedient, makes it easier to read, easier to write if we just drop the negation signs as soon as we can. Right? So if we drop double negations, rather. And so we end up with this. So here we have a negated conditional, right? And, well, we have a rule for getting rid of negating conditionals. If we scroll up, up, up. Negating conditionals, right? So if we have a negated conditional, we can rewrite it as the conjunction of the antecedent and the consequent but negated. So scrolling. Okay. So we would get QR and P and not Q, right? So the whole thing's an alternation. So if we wanted to rewrite everything, we would just combine the two sides. The dots here are going to be tricky. Or Q or R, and R or Q. And then I think we need 3, but I'm going to go with 4 just for emphasis. Or Q, R, and P, and not Q. Okay, So that, I'll zoom in so my handwriting is maybe a little more legible. That's one of the things that we could get if we applied our equivalency replacement rules to this original schema, right? The left side's so much bigger because we broke up this biconditional and there wasn't a biconditional on the right side. So hopefully that makes some sense. Actually, I'm going to come up with one more. Or actually, I could... No, I'm going to come up with one more. Okay. Okay, here's another monstrous, horrible, cumbersome schemata that I would not be happy to run into on a test. So the whole thing is a negated biconditional, right? And if we look up at our rules for eliminating negated biconditionals, right? We just drop the negation sign and negate a side of our choosing. So what we do is, the way that I'm going to do this, just for illustrative purposes, is I'm going to negate this right side. So keep the left side the same, not D, then A, B, C. Right? Oh, yeah. Okay. So let's work on the left side first. Again, because all of these laws apply to kind of any independent group or interior component of our big schema, we can work on little pieces at a time if we want to. That's perfectly fine. So this is an alternation, and it's negated. So we're going to be able to apply De Morgan's law. And if we do that, we get not P and not Q and R, right? Hopefully I'm not making a bunch of mistakes here. Then we can only do one thing here, and we have to do it to this. We can apply the other De Morgan's law. So we get not P and not Q or not R, right? So we can distribute over that. But let's see if I can get the whole thing in a normal form without too much work. I will, but let me look at the right side first. You don't know what a normal form is. Don't worry about it. You will. So here we have a negated conditional. And if we want to eliminate this negated conditional, this goes to, well, the antecedent stays the same, turns into a conjunction with the consequent negated. So not A, B, C. Right? Okay. So what do we do? Here, well, we can apply De Morgan's law to the right side conjunct of this. And if we do that, we get D and not A, or not B, or not C. Right? So let's... Oh, this would be a good example to do distributivity. So, yeah, let me work this out real quick. So what we're doing here is we're distributing conjunction through alternation on both sides. And so how that's going to work is, I'll just show you. Double check to make sure I'm right. Again, this is one of those things where I'll make mistakes. Right, so, okay, yeah. So this will turn into not P, not Q, or wait, yeah, that's right. Not R. Right, so that's how we would distribute there. Similarly on this side, we get D and not A, or D and not B, or D and not C, right? And then the whole thing's connected with a biconditional arrow. we could eliminate the biconditional, I guess. Screw it. Let's just do it. I would never give you something this long on a test, but I suppose it's good to know. Right, so if we wanted to distribute, or we wanted to get rid of the biconditional, well, we have to, this is going to be very long. It would be not P, not Q. I'm just doing parentheses temporarily because I don't know. I'm not sure how the grouping is going to work out on this yet. And okay, actually, I do know how the grouping is going to work out on it. So this will work. And then the second way around is just, or the right side is just going to be the other way around. So D not A or, oops. B or C. Oh, that should be negated. Right, and so that is, wait, why is there a conditional there? That shouldn't be no, wait, yeah, no, that's fine, I'm an idiot. Okay, and we could, if we wanted to do more stuff, I don't have the space to do too much more, but we could also eliminate these conditionals, and we could distribute everything through, I'm going to stop here because I think that's enough of an example. So these are the examples that I've been giving you are really cumbersome and complicated. In terms of actually having to apply these, you won't have to apply them to schemata that are nearly this complicated, but hopefully you can follow everything I did here, and hopefully this is enough for you to try the exercises. Again, there's not really any more, I can't like show you any intermediary steps here. So what you got to do is you got to try the exercises, and you got to just do enough of these until you get the application of the rules down. If you're confused at all, send me an email. This is probably a chapter where it'd be very helpful if you, if you keep getting something wrong on a quiz and you're not sure why, or if there's a homework assignment that you just don't even know where to start. Let me know. But study all of our equivalency rules, and hopefully this isn't too bad. I'm postponing Module 8 till next week, and all that Module 8 is, by the way, just looking forward, is using these laws to get things in a very specific form. So if you can use all of these laws and you know how to use these equivalencies to transform schemata, Module 8 will be really easy. If you don't, it'll be really hard. And so will like most of the modules for the rest of the course. Anyway, with that, good luck. Please let me know if there's any questions, if there are any questions or concerns. And if you need any more help, I'm more than happy to do a Zoom office hours at a time that I don't normally hold them. So let me know. Good luck. See you next week.